Okay, let's go ahead and begin, please. Couple of announcements. First one is to hopefully get this to work.
It might just click on the slide.
Again. No. It's okay. I'll use this. So if we can go ahead and please pass your homework assignments that way. Before you do, make sure you have written your flock number, which is your team number, where it shows on, I think it's the second or third page. So be sure you have your team number written in there. And then pass them to the right, or that way for you. To your left, my right. Okay, are they all in? All right. Cyber Sheep decisions. Wonderful for a Friday. So now you have to do that every time that sheep comes up. Well done. Cyber Sheep decisions are due tonight at 7 p.m. along with your statements, your justifications for how you're taking your decisions. Okay? Next topic, if this will work. We have this thing called an exam. It will be a week from today. We do have a review session that is being planned for Tuesday of next week that the TAs are very kindly going to hold. We have posted a practice exam which does include a sheet that is the equations that you more or less can also expect to see on the exam. Again, my strong recommendations, as would be Dr. Peterson, is that you use that exam as sort of a final preparation. So there's a version without answers, and then there's a version with answers. So prepare, and then use that quiz as sort of the back end of your preparations to get you ready for a week from today. Okay? Now, I know it's very hard to try to find a time that fits everyone's schedule. And so we're going to take a bit of a vote on that. So yank out your clickers if you would. And those are going to be your options. 5 to 7 p.m., 6 to 8 p.m., or 7 to 9, A, B, and C. So please enter your enthusiasms. Tuesday, October 30th. Everybody voted? Everybody good? All right. So it looks like a couple of you are coming in the middle of the night, but the rest of you appears to be the 5 to 7 p.m. session works best. So that will be the plan for Tuesday of next week to prepare for the exam. Okay? Okay, last time we talked about some ideas of sources of information. I'll review a little bit about that when I talk about accuracy to emphasize those ideas, but it was about where information comes from, how heritable it is. Is it on the individual itself, on its progeny, and if it's on relatives, what is the relationship among those relatives? Because all of that coalesces to have an impact on how accurate our genetic prediction is. And we talked about a couple of equations that we use in this context. What is this B, BV dot P asterisk? That is what kind of a coefficient? What is that called? That's a regression coefficient, right? So it's all about trying to predict breeding value from some source of information. Okay, say with me, guys. It's all about predicting breeding value from some source of information, and we multiply that value by the deviation from our population mean. So that P asterisk indicates the source of information we're using to evaluate an animal, and the P with the bar over it is that mean from which it's being deviated from, and that often is a contemporary group. We talked a little bit about how important contemporary group can be. And then we use that, we calculate that accounting for several things: the heritability of trait, how much information we have. Big R is what? It's the relationship of the animal with the source of information that we're using to evaluate it, right? So if it's on the animal itself, big R is going to equal what? So 1. If it's on its half sibs, what is big R? It's going to be a quarter, right? That's the genetic relationship between an animal and its half sibs. And then we have this bit on the bottom that also has the number of records, and then we have this thing that's called RP asterisk, and it's going to be one of 3 things, right? It's going to be the repeatability of the trait if the information that we're using to evaluate the animal is repeated records collected on itself. It's going to be related to, it's going to be T, that interclass correlation that you had the opportunity to practice a bit with in lab. It will be that T if that information is coming from a group of half sibs or a group of full sibs. Okay? And we need to take that into account. Now, finish up an example related to that. So depending on the source of information, it will impact that regression coefficient, and we use that to predict breeding value. And then we also talked about this idea called accuracy. Try to put this in one more spot to see if it might work for us today. Nope. And that looked like this, where we're basically taking that regression coefficient and we're multiplying it by the, that value of R, which again is relating the animal to the source of information being used in its evaluation, and we take its square root. Okay? And in class, I worked an example in which we used one or multiple records on an animal itself. And I want to extend that a little bit, what I've written up on the side of the board, to kind of show you what the consequences are when we have different amounts of information from different sources when we do our evaluation. And so what I'm going to do is, it turns out this bull that we've talked a little bit about before, this genetics by design that I'd used in a breeding program elsewhere, it turned out that he had 15 daughters, or 16 daughters actually, one of which is the animal that we were using as our illustration before, that fourth heifer. But he had 15 additional daughters that we measured docility scores on. And so one thing we could do is, if, for instance, we didn't happen to measure temperament on the heifer we are interested in, could we not use the information on her half sibs that are related because they all came out of that bull as a way to evaluate her? We can certainly do that, and for many traits we have to. Things that involve slaughter of an animal, you typically can't evaluate that on the animal itself, right? So sometimes using half sib information is inherently necessary. So on the board, kind of want to work through a couple ideas to draw that story together. You might remember, heritability of this evaluation shoot score was about 0.3. The repeatability was 0.4. And the C-squared, which is that common environmental effect, so that effect that is making these half sibs look more alike because they come from a family, is about 0.025. And as a reminder, for half sibs, particularly animals that are out there grazing, that are in different parts of a pasture or field, typically that common environmental effect is pretty small. And so that C-squared is pretty small in this case. So let's take a look at this in terms of this illustration. All right, got statistics down this one column. N is the number of records. RP asterisk is that value. Let me back this up so it's easy to see. So RP asterisk is this value down here in the denominator, right? Okay. If that gets bigger, what tends to happen to the size of that regression coefficient? Gets smaller, which means we're not getting as much information about the true breeding value from our source of information as that gets bigger, right? Okay. So RP asterisk, we've got that regression coefficient that's up there as well, and our accuracy. So those are going to be our 4 rows of our table. So last time when we were talking about this, I used an example where I had 1 record on the animal or 3 records on the animal, right? That was what we thought about. Turns out RP asterisk doesn't matter if we only have 1 record, because remember, if we have this n minus 1, this thing becomes 1 minus 1, so that ends up being 1. N is 1. In this case, what would R be if we're basing our evaluation on the animal's own performance? 1, right? So it turns out in that case, the RP asterisk doesn't matter because it cancels out. And if we do all of our math, it turns out that's 0.3, which is, on the single record on the animal, our heritability, right? That's how that boils down. When we move to 3 records, now we do have repeated information on that heifer herself. Turns out that our RP asterisk in that case is the repeatability. And I think you're comfortable with that now. We have repeated measures on the animal, so it makes sense that we need to account for the fact that we have those repeatedly measured. So in that case, our RP asterisk becomes R, the repeatability, which is 0.4, right? And so 0.4 is going there in the denominator. I'm taking account of the number of records, 3 now on this heifer, 3 minus 2, and that goes to 0.5. Question: is anyone surprised by the fact that as we moved to 3 records, we had a little bump, if I may, in that regression coefficient? Shouldn't be surprising. We know more, right? That's all that's really reflecting. We have more information that we're using. So it should be bigger, right? Rather than 1 record, we've got 3. So what happens when we do the accuracy? Well, the accuracy is the square root of that regression coefficient times R. R in this case is still what for both of those instances? What is capital R? We're basing it on the animal's own record or on repeated records on the animal. So what's its relationship with where the information is coming from? 1. It's on itself, right? So capital R is still 1. So that hasn't changed. So that's 1 here and 1 there. I brought down the regression coefficient. I took the square root. And I get something that looks like this. So I think, again, unsurprisingly, the accuracy has gone up, right? We know more. We've got 3 records rather than 1. And that's what's being reflected in that case. Okay? What happens, though, if we, for some reason, don't have a record on that heifer herself? But, as I said, I did have it on 15 of her half-sibs that came out of that one bull. I can use that to try to predict that heifer's breeding value for shoot score. So in that case, my RP asterisk goes to this thing that we call the interclass correlation, right? T. In this case, it's half-sib, so that's why that's THS. And as a reminder, that equals RH squared plus C squared. Really key question, and I know the TAs focused on this in labs this week. Is that R, or at least its value, inherently the same as the value of that R or that R? Yes or no? It's really important to keep straight. I hear some no's. It is not. It is not. Okay? This R, as a reminder, is the relationship between the animal and where the information is coming from. This R, although it's still the genetic relationship, is the relationship among the animals providing the information. 15 half-sibs in this case. So what is R in that example for that statistic T? They're half-sibs. It's their genetic relationship. It's a quarter, right? Because we anticipate they share a quarter of their alleles in common, given they share the same sire. Okay? So we do our plugging in. My C squared was on the other side of the board. Turns out that value was equal to 0.1. Okay? So if we flow down through, we now need to account the fact heritability is still the heritability, but I have 15 bits of information. This quarter is what? That's the relationship between the heifer we're evaluating and her half-sibs, right? So by coincidence, it's still a quarter. But it doesn't have to be. It's because of the example that we're looking at. Okay? If instead, as an illustration, we were using information on the progeny of a bull, its relationship with its progeny would be a half. So the big R's over here would be a half. But if they're half-sibs, their relationships with one another would be a quarter. All right? So keep that straight. So if we go through and we plug in all our values, our 15 minus 1, we took our T half-sib down here, and we end up with a regression coefficient of 0.47. Okay? A little bit smaller, but that's what it is. But there's still a pretty key difference here. Let's move over to the accuracy, right? The accuracy is that regression coefficient times the R that relates the animal to the source of information, right? So in this case, the heifer we're evaluating has a quarter of relationship to the animals we're using to evaluate, her 15 half-sibs, and so the accuracy is 0.34. So what is kind of the bottom line story here? Is it better typically to have information on yourself than on a relative, particularly if they're a half-sib, to do your evaluation? Absolutely, right? The reason is you're only sharing a quarter of your genes in common with that half-sib. So you don't do as good of a job of prediction. Even with 15, which sounds like a lot, we're still not better off using that half-sib information. Okay? But there are times where we can do nothing else. Traits that are only measured in one sex, traits that involve killing an animal to collect the data. We can't collect many of those things if it's a male and it's a female trait, or if it's a trait that requires an animal being processed. So we don't always have a choice. Okay? All right. So going forward today, these are the things that I want to talk about. We may not get to all of it, but we'll make a good start. I want to say a little bit more about accuracy. Talk a little bit about moving from what we're doing as an illustration in class to what we do in practice in the commercial environment. So we need to talk about an idea called BLUP, Best Linear Unbiased Prediction. And I'll use an illustration that you've partly already seen from industry. And then finally, I want to get to contributions of genomic selection in the story, which is this really powerful tool that we're now using in our industry genetic evaluations. Okay, so those are the topics we're going to visit about. Okay, factors that affect accuracy. There are three main factors: the heritability of the trait, how much we know, the number of records we have, and the relationship between where the information is coming from and the animal we're evaluating. Those are the three things that typically matter. Okay? How much we know, how heritable the trait is, and the relationship between the animal we're evaluating and the information we're using in the evaluation. I like to see things as pictures, so we're going to use a picture. I have a number of records along the horizontal axis, and our accuracy, as we've already defined it, along that vertical axis. So accuracy is going up, number of records are coming off to on the horizontal, and we have three heritabilities: 0.1, 0.3, 0.5. Okay? So we'll look at traits with three heritabilities. So if it turns out that we have a very lowly heritable trait, a heritability of 0.1, we see this. Oh, important point. In this case, like the example over here, I'm evaluating an animal based on its half-sibs performance. I'm evaluating the animal based on its half-sibs performance. And if that's the case, I get something that looks like this. So I get a big advantage early on, up to, say about 30, 40 progeny, and then the thing starts to plateau, right? I'm going to hit 0.3 here in a moment. You probably have it on your paper there, but what do you think that curve is going to look like? Is it going to be steeper and flatten out sooner, or be less so? It's going to be a little bit steeper, right? But it plateaus a lot sooner, okay? The reason is, as the heritability goes up, we learn less from the additional information because the trait is already moderately heritable. So we're learning a fair bit from the first couple of records on progeny, so we only gain so much more as we collect more and more and more. This idea of marginal returns that you would have seen in most of your economics courses, it applies here as well. Okay? And if I go to a higher heritable trait, we get that same pattern, but it plateaus quicker. So if I have a trait that I know that is highly heritable, I'll tend not to invest as much effort into measuring more and more progeny than for a trait that is very lowly heritable. So if I'm worried about reproductive rate, I tend to want to have lots of information on half-sibs. If I'm worried about a fleece weight, I tend not to because the trait is moderately to highly heritable. Okay? So that's a relationship between number of records and accuracy. And the other scenario I want to show, if I can hit this, is this idea. This is something, if you want to do at home, to think through, if you like a little bit of math. The asymptote, when you have half-sib information, in terms of accuracy, is 0.5. You could have a billion progeny, or a billion half-sibs of the individual. You're never going over 0.5. So if you like playing around a little bit with numbers, you can show why that must be true. Okay? So that is the asymptote with half-sibs. All right. Let's take a look now at this idea of where information is coming from. Okay? Individual itself, from a half-sib, one of them, or a progeny, one of them. So we measure the individual, or one of its half-sibs, or one of its progeny. 3 options. Lowly heritable trait, we see something like this. As I'm hoping you're expecting, given this story over here, the information on the animal itself caused the highest accuracy, right? Turns out the half-sib information, lowest accuracy. Why does it make sense that on a progeny it's in between? What's the genetic relationship between that animal and its progeny? A half. What's its relationship with its half-sib? A quarter, right? So we learn more from a progeny than we do from a half-sib. And we learn less on both of those than measuring the animal itself. Okay, so that relationship should make sense. Heritability goes up. Everything goes up along with it. Okay? Higher the heritability, the more we learn about the animal's true breeding value from the data or the phenotype that we have. So our accuracies go up, and it becomes even more so as the heritability increases further. So the advantage of having individual over progeny over half-sib information persists as heritabilities increase. Okay? So that's a way to think about how we emphasize information in our genetic evaluation. It's based on what we learn. Okay. But I have a question for you. I'm still evaluating that bull or heifer. That's what I want to do. I want to accurately predict its merit. And we've talked about bits and pieces of information. So my question is, why not use all of it, right? We learn something from everything that we might record that relates to that animal. So it seems pretty silly not to try to utilize everything we record in our prediction, right? That seems like we're wasting information if we don't. So there was a revolution in technologies that came about, 20, 30 years ago that allows us to actually do that really quite seamlessly in terms of folks using these genetic evaluations. So I'm not going to ask you to do this, but I want to give you the principles. See, Ben is happy about that. The principles in mind in terms of what it means, what it does to try to use everything together. And that's called best linear unbiased prediction, okay? Or BLUP. Best linear unbiased prediction, or BLUP. And it is a method where we predict an animal's breeding value just like we've been trying to do. But now, rather than taking 1 or 2 bits of information, we use all of it, and we use all of it at the same time. Do you think that will improve accuracy? Absolutely, right? We just know a lot more. Keep in mind, what we gain with some of the genetic or some of the genomic tools is really just a continuation of that. We just know more about an animal to use to predict its breeding value. It's the same concept. It's just different and more information in our evaluation. But BLUP allows us to use everything we might know on the animal itself, its progeny, ancestors, siblings in our evaluation. Okay? Here's some features. It can account for differences in the genetic levels of contemporary group. Okay? So by so doing, or the way it goes about doing so, is it accounts for the fact that we will have relatives performing in different contemporary groups. And you're doing that right now. I guarantee you're doing that right now when you're playing cyber sheep. How many of you, if you want to fess up your program, are using AI sires or purchased rams in your breeding program? How many of you? I think most of you are, from what I can tell. So what does that mean? Other people are probably using at least the reference sires in their own flocks, right? And so as a consequence, they've got lambs coming out of the same rams as you do, and as a neighbor does, and as a consequence, you're comparing the performance of those animals across different contemporary groups. So you're doing that, and BLUP is really effective in taking that into account and improving the quality of the evaluation. Okay? And also, by going about doing that, you're able to separate or disentangle those things that are environmental, management, feeding, seasonal conditions from those that are genetic. And that's really important to do if we want to equitably compare the merit of our animals in our cattle, sheep, goat, whatever kind of operation we're talking about. So BLUP is really effective in dealing with contemporary groups, given the sharing of genes across contemporary groups. It also deals with a genetic trend. Okay? Counts for the fact that younger animals are better than older animals, and includes that in the way it conducts the genetic evaluation. You may remember way back at the start, I showed you genetic trends in Angus cattle, and weights were going up over time because of selection. BLUP is able to handle that properly in the evaluations that it does. Okay? It also uses everything we know about animals in our population for the trait we're evaluating. So and it also uses information on genetically correlated traits. So we'll get into talking about correlated traits early next week, but genes that impact birth weight also impact weaning weight. Okay? Dr. Peterson introduced the idea of pleiotropy. We'll talk more about that. So we can learn about birth weight merit from weaning weight performance and vice versa. BLUP will do that automatically. So it uses information from related traits or pleiotropic traits quite well. And it does it all in one kit and caboodle. And as a consequence of that, it's really demanding. If we think about our current dairy cattle evaluations, Holstein, my goodness, it's using multiple traits on millions of cattle at one time in the prediction. That makes most computers smoke and steam in any best of circumstances. So a lot of the development of these tools have evolved alongside developments in our computational technologies, because you have to have a really fast, powerful computer to get it to work. Okay? It also counts for non-random mating, mating better sires to better dams. In reading your explanations of what you did in round 1 of Cyber Sheep, most of you did one of two things. You mated your best rams to your best ewes. That's called positive assortative mating, best to best. Or some of you trying to reach some intermediate weight, bred your best to the worst of the ones you selected. Your highest EBV to your lowest EBV of the ones that you chose to keep. That's referred to as negative assortative mating. And you're trying to achieve an intermediate weight based on that scenario. BLUP handles that. It doesn't care how you mate them, it's going to take that into account. Because none of that is random. You're very determined or dogmatic, if I may, in how you made your mating decisions. Okay? And interesting enough, it provides predictions on everything. Whether the animal's been recorded or not, whether it's alive or dead, it gives you an information about it. This is becoming really important as we're incorporating in our genomic tools, because we are now able, in some limited species, to make selection decisions when animals are in utero. And I think I gave a hint of that earlier on. So that animal has never had the opportunity to perform. It's not even born yet, and we still can get a prediction of its merit based on these technologies. Pretty powerful. Okay? BLUP is unbiased. Okay? It has in its name unbiased prediction. So what do we mean by unbiased? I'll show you an illustration in the large-scale genetic evaluation to emphasize it. Unbiased means that as we get more information, that animal's prediction is likely to go up as it is to go down. It's not directional. So more information doesn't inherently mean that animal is better than we thought it was or worse than we thought it was. It's more information, but it could imply the animal is better or worse than we thought it was on past information. BLUP takes that into account. It is unbiased. It doesn't have a direction as you add additional information. Okay. I want to take the last few minutes to now kind of transcend to linking this to what we do in large-scale genetic evaluation. And as my illustration, I'm going to use the bull that you all liked from earlier in the term. Okay, so I want to illustrate some ideas of what we've been talking about and how it is actually incorporated in what we do within our industry. Okay. So we talked a little bit about this, but I want to remind you of what you learn, what you get back when you go to, in this case, the American Angus Association and seek to get genetic information about a bull. So you'll get something that looks like this. Okay, so here's the bull's name. It has his birth date, so that bull was born in 2012, its tattoo, and its registration number. That asterisk adjacent to the number means that that bull's parentage has been validated based on genomic information. It's either been done using a parentage panel, or it's been done using what we call a low-density SNP chip. So the parents aren't only written down because somebody thought they were mom and dad. It's been verified using genomic tools. In our industries, particularly beef, that's going to almost become a requirement sooner than later as sort of a prediction of what will happen. Okay? So that's what that means. Okay? And then we have a series of genetic conditions. And I'm going to show you a couple of these just to remind you. These are recessively inherited, or these are simply inherited traits where a recessive allele usually causes something pretty bad. It's either lethal or at least isn't very good. And so what happens in the evaluations through genetic testing, just like you're doing with spider allele if you so wish, they give information back about the bull and whether it's a carrier or a heterozygote for a condition. So AM, I'll explain what the different things are, or some of these, but the F at the end of each of those sets of digits imply he is free, he is a non-carrier of the recessive allele associated with any of those conditions. Okay? So let me show you the first one. This one came out in about 2008. It was a big deal when we were out in Virginia because the herd where this came from was one of our local seed stock operators. What's really cool about this, to tell you how genomic technologies evolved, Dr. Peterson may know exactly the time frame, but I think it was within about a month or two, they identified where that mutation was and developed a test to put into industry. The response rate was remarkably fast to move from a condition that was causing this curly calf syndrome to a method to genotype test for it in order to try to address it. So with curly calf, what you tend to see is some curvature of the spine and the legs. Sometimes these legs are extended, sometimes they're curved in. There's often a cleft of the jaw. The calf will be dead at birth or a couple days thereafter. So clearly this is something you want to avoid, right? That's not going to do your herd any good. So that was found and a test developed and addressed very, very quickly. This one is called contractural arachnodactyly. Any of you who might do any hunting, folks look at that and think it looks like the back end of a deer, a fawn, or an elk near birth. And you see this kind of down in the haunches. One thing that may not be as clear, these calves do survive by about 6 months of age. It isn't nearly as clear as you see here, but they tend to be pretty tall. And part of the reason they tend to be tall, it may not be entirely transparent, but those pasterns are a bit elongated, so they tend to be tall and thin and poorly muscled. So they have this contraction of the back end. It sorts itself out a little bit as they grow older, but those will always be a poor doing calf. Okay? Again, a condition you want to avoid. Okay? And another one, which is particularly dramatic to show you, is this developmental duplication where animals have additional appendages. Typically that is lethal early on, but clearly a condition one does not want to have in their herd. And there are several others up here. Let me see here. The D2F has to do with dwarfism. The M1F is the myostatin gene associated with double muscling. What else do we have here? We have a hydrocephalus gene. There is, this one is an ocular disease. Has anyone seen a calf that has kind of a blue tint around the eye? That's what that relates to. And the last one is often referred to as marble bone disease. They have really brittly bones. That's a pretty nasty one as well. Okay? So they provide all this information because it's important for people to have when they are thinking about animals they keep as replacements. Okay? And then on the proof, you get some additional information, and I want to talk quickly about just one part of that. Okay? We have genomic information. We have a parentage SNP. Remember I mentioned that there is an asterisk up there implying genomic information is being used in his evaluation of his parentage. The HD50K is a panel that has 50,000 markers. That's the Zoetis product. Angus uses either Zoetis or Neogene gene-seq-based products. So that's what that is. And the genomic progeny is the number of progeny of that bull that has genomic information on it. Okay? So about 440. Okay? And then you're also given information about the pedigree, similar to what you can actually get if you do the pedigree download in Cybersheet. You learn something about the parents, the grandparents, and the great-great-grandparents, and they provide some information about other evaluations of this animal. The asterisk parents qualified means parentage has been verified based on genomic evaluation. I briefly talked about the Pathfinder. I think early in the course, Pathfinder is all about trying to find cows that are more productive. For a cow to be a Pathfinder, she has to calve in a very narrow window around the average of the herd. Okay, she needs to produce, to do that sequentially in 3 calving events, and her calves need to wane at 105% of their contemporaries. So she has to regularly conceive and produce a calf that weighs more than average. So if she does that 3 times, she's a Pathfinder cow. A bull that has 5 Pathfinder daughters is a Pathfinder bull. Okay? So it's all about trying to bring in some issues related to the productivity of the cow. Okay? And then you get some information on actual traits. Okay, we've been talking a lot about docility. That's this prediction based on BLUP for docility scores. As a reminder, you get the EPD, so that's 1/2 the breeding value. You get the accuracy, so 81%. Take a look at what we have over here. So those accuracies are certainly a lot higher, right, than what we've been able to obtain in our small example, because those bulls have a lot of progeny on the ground, a lot of relatives. Okay? The 1% is where refers to where it is in the league table, so it's in the top 1% in terms of quality in that example for docility, and it has 512 offspring. And we could go across all those. You've got birth weight, weaning weight, yearling weight, residual average daily gain and dry matter intake, that's performance post-weaning, yearling height, scrotal circumference, and our docility score. And all of those are described within the evaluation. But I want you to see one point that's really important. Notice the date I have up here. I downloaded that last night, or yesterday, and they put out a new evaluation every Friday. So this is from the previous Friday. So that's what that is, okay? You may remember the first one we looked at was about, what, 2 months ago when this course kicked off, month and a half? So this is what's gone on between now and then. Okay? Now and here, excuse me, I said that. So here we go. This is for a calving ease direct, so that's whether or not a positive score implies that there's less difficulty at calving. A small change in accuracy. Okay? A week ago it actually looked a little bit better, and that change is coming about because it went from having information on 468 to 512 progeny. Okay? So we know more. It's being incorporated in the genetic evaluation, impacting breeding values, accuracies, everything we have. Okay? Keep those numbers in mind for a moment. All right? So that's on productive traits. If we now look at some of the maternal traits, so this second set is all about the performance of daughters of that bull. So we have things like heifer pregnancy, calving ease, maternal milk. You can't really see that, but I think, oh, that's the number. So the 44 here is the number of herds in which that bull has had daughters. 136 is the number of daughters that have been evaluated. Then we've got mature weight, mature height, and we'll talk about indexes at another point in time. So take a look at, think about what we saw a moment ago, and let's take a look at a similar comparison now. Okay? Month and a half ago, those are the estimated breeding values, or the expected progeny differences. And we've got the accuracies, and we've got the percentages, and we have the number of records. So going from 7 to 10 records, right, is proportionally a lot bigger change than going from 480 or whatever it was to 500 plus. And I put that up there because I knew I'd forget, right? So notice that on this trait, where we're still pretty early on in getting information on his daughters, 2012 born bull, even what seems to be small changes in numbers are having a pretty big impact on its proof, right? Remember all those curves we've been looking at? At the lower end, when you start collecting that first information, you're making more benefit, and then it plateaus. When we're going from 7 to 10, that's at that end, right, of that curve. When we're going from 500 to 500, we're already out there where additional information will start making less difference. So when you're evaluating these data, when you're thinking about performance, it matters a lot as to how much we know about an animal at a time. So think about that when you're doing the evaluation. Let me show you one more picture, or one more part of this. Whoops. I hope. So the last set of information is on carcass. We've got carcass, marbling, ribeye area, fat depth. Notice there's a lot less information on the carcass than there is on these other traits, and that makes sense. We will stop there. Have a good weekend. We will pick it up on Monday.